Good afternoon. We are starting on lecture 6 of Power Electronics and EV Drives course. We had seen three-phase full bridge rectifier or diode bridge rectifier, which is an uncontrolled rectifier in the last class. And we said that the output voltage, V load average, in this particular case was actually 3 VLM divided by pi, where VLM was line voltage peak of the line voltage. That's what we said. So this is line voltage peak. So today we are going to discuss three-phase fully controlled rectifier. Or we are going to call this as full converter. Three-phase full converter. So which means we are going to have control in the positive side as well as negative side. Negative half wave as well as positive half wave. So this will be made up of SCRs. So we are going to have 6 SCRs connected in bridge fashion. So we have one SCR here and one more SCR at the bottom. Similarly, we have one SCR at the top in the second phase, one more SCR at the bottom in the second phase. This is the third phase where we are going to have one SCR like this and one more SCR like this. Now we will connect the load here. Let me just show the load generically like this. It could be R, RL or RLE. So I'm going to have a circuit like this. Now I'm going to connect A phase voltage here, B phase voltage here, and C phase voltage here. So I'm going to call this as, say, VA. I'm going to call this as, say, VB. And I'm going to call this as VC. And I'm just connecting them together with the neutral point like this. This is the neutral point. Okay. Now let me call this device exactly like what we had numbered earlier in the previous rectifier D1, D3, D5, D4, D6 and D2. The same thing I am going to write here. This is going to be T1. This is going to be T3. This is going to be T5. And this will be T4. This will be T6. And this will be T2. So this is how the devices are numbered, just like what we did in the case of the diode rectifier. Let me again draw the waveforms. This is VA and this is going to be omega t. And this is going to be VB. And let me show VC somewhat like this. So this is going to be 0. This is 60 degrees. This is 120 degrees. This is 180 degrees or pi. And this is 240 degrees. And this is 300. And this is going to be 2 pi or 360. Now, as far as the diode rectifier is concerned, we said in the upper device, whichever is the most positive, that will conduct at any point in time. Similarly, at the bottom device, whichever is the most negative, that will conduct at any point in time. That's how we talked about the diode rectifier. So if we call this as VA, this as VB, and this as VC, this is the point at which diode 1 was taking over. So this is the natural point of takeover of T1 in this particular case. So let me call this as delay angle equal to 0. If I don't give any delay angle, this is the point at which T1 would have started conducting. So my delay angle always has to be calculated from this as the reference point. So if this is the reference point, and if I am talking about a delay angle of, let us say, 30 degrees, this will be the point at which I'll be firing the device. Rather than that, if I say delay angle of 60 degrees, this will be the point at which I'll be firing the device. So here is where I will fire T1. And from there, exactly 60 degrees later, because even if you look at the diode rectifier, very clearly D1 was taking over at this point, D2 was taking over at this point, D3 was taking over at this point. So all of them are displaced from each other by 60 degrees. So if D1 is starting at omega t equal to 30 degree point, D2 will start at omega t equal to 90 degree, which is 60 degrees away. D3 will start at omega t equal to 150 degrees and so on. So everything is going to start staggered by 60 degrees. The same thing holds good here also. So I should actually fire T2 here, and I should be firing T3 here, and I should be firing T4, and T5 will be fired at this point, and T6 will be fired at this point. This is how each of the devices will be fired. So when I am firing T1, T6 must have been already conducting, hopefully. So if I say T1 is fired at this point, and T6 is already conducting, T6 belongs to B phase. So I should have between these 2 points, whatever is the voltage, that should be coming up as the output voltage, because when T1 is fired, I will have VA connected here, and when T6 is already conducting, I will have VB coming up here. So between VA and VB, whatever is the available point, available voltage, that is what is coming up across the load. So across the load, what is available, if I call this as V load, that V load will be exactly whatever is between VA and VB when T1 and T4 are conducting, T1 and T6 are conducting. So when T1, T6 are conducting, it is going to be VAB. Whereas when I'm going to have T1 and T2 conducting, T1 and T2, when T2 is fired, it is C phase. This T2 is connected to C phase. So between VA and VC, whatever is the voltage, that will come up during this particular T1 and T2 conduction period. So that is going to be VAC. And when I talk about T2 and T3 conducting, so T2 and T3. T3 is fired here, and T3 corresponds to VB, and T2 corresponds to VC. So I will have VB and VC. These are the two voltages. Those are going to be appearing across the load. So I will have basically this is VB and this is VC. So I should show it as though this is the voltage that is coming up during this interval. And again, when 4 is fired, so I should say this is VBC. Similarly, when we talk about T3 and T4 conducting together, this is going to be VBA. and T4 and T5 conducting together. 5 corresponds to VC and 4 corresponds to A, so that is VCA. And T5 and T6, when we are looking at it together, T5 belongs to C phase and 6 belongs to B phase, so it will be VCB and it will be repeating itself subsequently. So when 4 is conducting, it is 3 and 4, we are going to have this as the voltage. This is going to be the voltage that is available during that period and so on. So if I try to draw the voltage across the load, I'm going to again show this as omega t. And I am going to show this point as VA, and here is where VAB will end. So I will have here, you can see the magnitude is very large and it is ending up in 0. And it is after all again a sinusoid. VA minus VB will also be a sinusoid. So this is the way it is going to be. And the next one, which is coming up corresponding to T2 and T3, again, this will be somewhat like this. And we are going to have the voltages continuously coming up like this for every 60 degrees. Only difference is during this period, it is going to be VAB. During this period, it will be VAC. This will be VBC. This again, if I try to write, so this is VAB, VAC, VBC. Then I can again draw the next segment like this. So that is going to be VBA, and I have to draw 2 more segments here. So I'm going to draw one segment somewhat like this, and the other segment will be only half. It would be increasing further. So this would be somewhat like this. So this will be after VBA, it is VCA, and this is going to be VCB. So this is how it is going to be as far as the output voltages are concerned. So this is the output voltage waveform. So I can calculate again what is the load voltage average value. So if you may recall, in the last fully controlled diode rectifier, full converter with diode, we said we have to start from pi by 6 to pi by 6 plus pi by 3. That is, whatever is the beginning, from there we have to have another 60 degrees added as the upper limit. So pi by 6 is the starting point because we said the starting point happens to be here, which is corresponding to half of the 60-degree interval. So that is why we called this point as pi by 6. So if you look at what we have drawn here, the natural point of conduction is this, which is corresponding to omega t equal to pi by 6. But how much I have delayed, that depends upon the delay angle alpha. So I should write it is starting from pi by 6 to plus alpha. So pi by 6 is the natural point of conduction had it been a diode, and alpha is the delay I am giving in terms of the delay angle when I am giving gate pulse to that particular device. So on the other side, it is going to be pi by 6 plus alpha plus pi by 3. This is the entire thing that is going to come up, and I have to average it over pi by 3 because every 60 degrees things are changing. Here we had 1 and 2 conducting. Here we had 2 and 1 and 6 conducting. Here we had 1 and 2 conducting. Here we had 2 and 3 conducting. This is 3 and 4. And we had 4 and 5 and 5 and 6. This is how the conduction of the devices take place. So I should write this as Again, if I am talking about pi by 6 plus alpha, this is pi by 6 plus alpha point, and this is pi by 6 plus alpha plus pi by 3. So this is going to be VAB d omega t. And in the last class itself, we said if I am doing the integration of VAB, but I am taking the reference as VA, then I have to write VAB. VAB leads VA by 30 degrees. So it is sine omega t plus pi by 6. And the quantity, the magnitude will be root 3 times Vm, where Vm is phase voltage peak value. So I should be able to write this as 3 by 3 divided by pi integral of pi by 6 plus alpha, and pi by 6 plus pi by 3 is pi by 2. So let me write this as pi by 2 plus alpha as the upper limit. And I can write root 3 times Vm. Vm is the phase peak, sine omega t plus pi by 6 d omega t. This is going to be the expression that needs to be integrated. So this will come out to be 3 root 3 Vm. Instead of root 3 Vm, we can write 3 VLM by pi, where VLM is line voltage peak. This is going to be line voltage peak. So 3 VLM by pi, and this is sine omega t plus pi by 6. So I can write that as cosine omega t plus pi by 6. Its integration. And because there is a minus sign inherently, I put the lower limit on the top and upper limit on the bottom. So I can write this as 3 VLM divided by pi, and I can write cos of pi by 3 plus alpha minus cos of pi by 2 plus pi by 6 plus alpha. So I can write this as, when I simplify this, I should be able to get this as cos alpha. When I simplify this, please verify this. So 3 VLM divided by pi cos alpha is going to be the average voltage expression for three-phase fully controlled converter. It is going to be the average voltage expression. So I can again draw the current corresponding to this particular R load case. R load case, you will have the load voltage and load current exactly looking the same. So if I am talking about load voltage like this, load current I should essentially draw almost with a similar variation. Only thing is divided by resistance. Depending upon what is the value of resistance, I am going to have a lesser value or whatever. So this is going to be the kind of waveform I'm going to get as far as the current is concerned. So the green color one is current, I load, and this one, this is going to be V load. So this is V load and this is I load. And if I am going to have R and L, if I'm going to have R and L, then again I will have the equation which governs the dynamics of the circuit will be Ri plus L di divided by dt equal to VAB for omega t ranging from pi by 6 plus alpha to pi by 2 plus alpha. That is the integration limit we have put up. So I am putting the same limit. So when I am talking about pi by 6 plus alpha to pi by 2 plus alpha, I am going to have, during that time, I'm going to have VAB appearing across the load. That's what we said. VAB appears across the load when 1 and 6 are conducting, which will be from pi by 6 plus alpha. This point is pi by 6 plus alpha, and this is going to be pi by 2 plus alpha. So this is the way it is going to be. So in this particular case also, when VAB minus RI equal to 0, that is when we are going to have LdI by dt equal to 0, or I reaches maximum. So the current is going to reach its maximum value at that point. So I'm going to again show this in a little enlarged way. So let us say this is the load voltage that I'm going to have. So this is probably the first, and this is the next one, and this is going to be the third one. And this is going to be the fourth one, and so on. So we said that actually, if you look at this waveform, VAB comes as the third one. So let me say this is what VAB. And before that, it is going to be VCB. And before that, it is going to be VCA, and so on. So this is how it is. And this is the point at which it is pi by 6 plus alpha. And this is the point at which it is pi by 2 plus alpha. So if I say that the current had been decreasing, maybe it is a continuous current, and current starts increasing from this point. So when it increases, maybe if I try to draw what is uh, I times R, I'm going to have it somewhat like this. So when I times R is meeting with this particular uh, Vm sin omega t or VAB, at that point, the current will start declining, because after that the current will, according to this, L di by dt is 0 when VAB and RI are equal to each other, or VCB and RI are equal to each other. After that, I will have the current declining. So current is going to decline like this. Then again it will increase, then it will decline like this. So you are going to see that the current has a waveform somewhat like this. This is how the current will be for RL load, because the exact equation, whatever we wrote earlier also, that is very much valid even in this particular case. When the load voltage is equal to Ri, that is when the current will reach its maximum value, and that's what we have shown. So correspondingly, if I try to plot Ri, I'm going to have something like this. So it is going to increase like this, and this will be Ri. So if I try to look at what are the devices that are conducting, let me probably draw further also whatever I am drawing here. So I'm going to have another, uh, you know, at least two of them coming up like this. So let me say here I'm going to have 5 and 6, whereas 6 and 1, this is 1 and 2, this is 2 and 3, and this is 3 and 4, and this is 4 and 5. This is the way it is going to be. So whenever one is conducting, I'm going to have a current flowing like this, flowing through the device T1, and it is going to go through the load like this. So the load current equal to IA when T1 conducts. Otherwise, I load will be equal to minus IA when T4 conducts. So when the negative device conducts, you are going to have actually the current flowing in like this, and flowing in the opposite sense. So if I am calling the source current or IA is in this direction, when T4 is conducting, IA and the load current are in opposite direction. And that is what I am saying here. I load is equal to minus IA when T4 conducts. So correspondingly, let us try to draw the current waveform. So when I draw the current waveform, I'm going to see that here it is only 5, 6, whereas here it is 4 and 5. So whatever is the current waveform I am getting, I have to draw the opposite of that in the reverse direction. And after that, when 5 and 6 are conducting, please note that 5 belongs to C phase and 6 belongs to B phase. So A phase is not involved at all when 5 and 6 are conducting. So I'm going to have literally zero current during that particular interval. But after that, 1 and 2 are conducting, and then 6 and 1 are conducting, and 1 and 2 are conducting. So for these two intervals, I should show the current like this. And then when 2 and 3 are conducting, I'm going to have zero current again. Whereas when 3 and 4 are conducting, I'm going to have a current which is exactly opposite to that of what was happening in the load. So I'm going to have the load current somewhat like this. So this is the way I will have IA. And if I draw IB and IC, I should have similar waveforms, but it should be extending, or it should be phase shifted by 120 degrees. So if I call this as omega t, and if I want to draw, so this is 1, this is also 1, and this is 4, and this is 4. This is also 4. So when I'm talking about B phase positive will start from here, and I should show as though during this portion it is like this, and again for the next thing it will be like this. So these two will be corresponding to device number 3. And device number 6 is actually shown here. So I'm going to have device number 6 current somewhat like this. And again device number 6 current somewhat like this. And for 60 degrees, nothing is going to show up in B phase. That is because I'm going to have 1 and 2 conducting here. Whereas whenever 6 is conducting, there will be a negative current in B phase. Whenever 3 is conducting, there will be a positive current in B phase. Similarly, I should be able to draw as far as C phase is concerned. Whenever 2 is conducting, I am going to have negative current. So I will have this current like this current like this, and it will be going down, and this will be 0, and this will go like this, and you are going to have. So this is the way you are going to have the current corresponding to C phase. So this will be 5, this will be 5, device number 5 conducting, and this will be 2, and this will be 2, and this is IC. Whereas this is going to be IA. So this is the way the currents look generally in the case of 3-phase fully controlled rectifier. So let me show this again. So this is a diode converter which we had already seen. Now, this is a three-phase fully controlled rectifier. Three-phase fully controlled converter simulation I am showing here. So you can very well see that the waveform what we have taken is very similar to what I had drawn even here. So this is 60-degree firing angle. The same thing holds good here also. It is 60-degree firing angle. So for 60-degree firing angle, I have shown clearly what is the phase voltage here and what is the phase current here. The phase voltage and phase current are what we had already drawn in terms of what I had shown here basically. So this is A phase current I had shown and A phase negative side current I had shown. So the same thing holds good here also. And here if you look at it, this green color waveform is IDC or load current. And this red color waveform is output voltage. And you can very well see that this is VAC and it is coinciding with VAC here. So before that it would have been coinciding with VAB and before that it must have been coinciding with VCB and so on. So this is the simulation corresponding to three-phase fully controlled rectifier showing the supply side current, supply side phase voltage, and DC side current and DC side voltage. Now let us try to take a look as to what happens if there is a DC voltage source. What I mean is, if I am going to have the three legs of the SCR converter somewhat like this. This is going to be the SCR converter and I'm going to connect it to R, L and the battery. This is the kind of load I'm connecting. Okay. So I'm going to connect VA here, VB here, and VC here. So let me call this as VA, this as VB, and this as VC, and this is T1, this is T3, and this is T5, and this is T4, this is T6, and this is T2. And let's say this is R, this is L, and this is going to be E. Now, let me probably take, let me try to draw the voltages again. And let me take alpha equal to 60 degrees itself. So let me try to write three-phase full converter feeding RLE load. That's what we are trying to show. So I'm going to have one phase voltage somewhat like this. This is omega t. And let me show this as the 60-degree interval. So the second phase is going to come up like this. So this is the second phase. And let me show the third phase somewhat like this. So this is the third phase. So this is going to be 0, this is pi, and this is going to be 2 pi. Okay. Now what we said was this is the natural point of conduction. So from here I have delayed it by 60 degrees. So this is where I am firing device number 1. So let me draw from here. I'm going to have for the next 60 degrees until here, I'm going to have VAB. And until here, I'm going to have VAC. And before that, for 60 degrees, I'm going to have VCB and so on. So I'm going to have this as the voltage output. So this is VCB, this is VAB, this is VAC, and so on. Now, on the top of this, I'm going to draw. So let me finish this also clearly. Now, on the top of this, I'm going to draw the EMF E. So this is what is E. Now I'm going to have the equation as VAB or VAC or whatever, that is going to be equal to Ri plus L di divided by dt plus E. This is how it is going to be. So I should say VAB minus Ri minus E when it is 0. That is when L di by dt equal to 0 or I is maximum. I is going to be maximum. So we are going to have actually the current somewhat like this. The current would probably increase from certain value and reach the peak somewhere like this, and then it will come down. Again, this will be the kind of current we will have depending upon how much is the inductance value, how much is the resistance value, how much is the battery value, battery voltage value, and how much is the peak of this supply voltage. So what decides? So the continuity or discontinuous nature of current will be decided by what are the values of R, L, Vm, E, and so on. Okay? So all these things are going to decide alpha also, of course, firing angle alpha. So all of them together are going to decide what is going to be the nature of the current, whether it will be continuous or discontinuous. So on the whole, what we can say is, compared to single phase converter, three-phase converter gets this voltage every 60 degrees. Every 60 degrees, the voltage gets replenished. Whereas in single phase case, we are going to have one voltage coming up like this from 0 to pi, and next pi only, pi to 2 pi only, again the second voltage is coming up like this. This is in full wave rectifier with diodes. Whereas if it is with SCRs, we are going to have the voltage only starting at some point which is corresponding to alpha, and it is going to go like this, and it will go into the negative side also and then jump up like this and go like this. This is the way I'm going to have the voltage. So the voltage gets replenished only once or twice in one cycle. So here it is only happening twice in one cycle. Whereas here it is happening 6 times in one cycle. So obviously the three-phase converter has, or three-phase rectifier has a better probability of continuous conduction as compared to single phase case. So always three-phase converter will have a better probability of continuous conduction as compared to single phase case. Let me take up, before we conclude this particular lecture, let me take up one of the questions I had given in the surprise quiz. So in surprise quiz, I had given a question that a half-wave diode rectifier is feeding a pure inductive load. So this is Vm sine omega t, and this is a diode, and this is a pure inductance. What was being asked was, what is the voltage across this inductance and what will be the current waveform, both. So V load and I load. What are these? And justify your answer. This is what was asked. So if you look at the diode conducting, it will conduct. Diode is supposed to conduct when it is forward biased. So diode conducts when it is forward biased. Only when it is forward biased. So we are going to have L di by dt is equal to Vm sine omega t when diode conducts. And Vm sine omega t will be positive for the entire positive half cycle. So if I just draw the voltage waveform, this is the way the voltage waveform is going to be. So this is Vs. And if I say that di by dt is going to be positive throughout the entire positive half cycle, I'm going to have the current increasing probably like this. The current will increase like this. And when Vm sine omega t is negative, whenever it is negative half cycle, I'm going to have again the current falling. So I'm going to have the current through the inductance somewhat like this. This is going to be the load current. And if the inductor current is continuous, it is not really becoming discontinuous at all. Whatever is the voltage here, that will come up across the inductance. Because when we look at load voltage is L di by dt. And L di by dt actually will be exactly same as this when we are talking about the inductance conducting, the diode conducting during positive half cycle. After the end of positive half cycle, because the current is at its peak value, the inductance is definitely going to release its energy. When it is releasing its energy, it will be actually plus here and minus here. So there will be something like a tug of war between the plus voltage of the inductance and because we are talking about negative half cycle now, plus voltage of the supply also. There will be a tug of war between these two. And if it so happens that inductance is winning over, then the diode will be still forward biased. So you will have this voltage completely coming across the inductance. So I should have even the reverse half cycle completely being translated at the output also. So you should have both positive half cycle as well as negative half cycle appearing across the load. So there is no rectification. So no rectification of input voltage is not going to be rectified at all. That is what it is going to be. Okay. So this is the answer for the surprise quiz question number 1. Question number 2, I had discussed already in the last lecture. Nevertheless, I will try to reiterate that. So if I am going to have a diode rectifier like this and it is feeding some load, single phase diode rectifier feeding a load, and if this is where I'm going to have the AC voltage connected. What was asked was, what will be the load voltage? If I try to look at the load voltage, what will be the load voltage if one diode conks out or two diodes conk out? If one diode conks out, so first subdivision was one diode is open circuited. So if one diode is open circuited, let us say this is open circuited. So I'm going to show this as open circuited. So now what will happen is, if I'm calling this as D1, this is D3, this is D2, and this is D4. D4 is not even existing. When the positive half cycle commences, you are going to have the current trying to flow like this, through this, and it is supposed to return through this. And there is no device existing here. It is an open circuit. So no conduction in positive half cycle. We will not have any conduction in the positive half cycle. So if I am talking about the supply voltage like this is Vs, then I'm going to have the output only during reverse half cycle. So this will be 0. And I'm going to have 0 again. Only during reverse half cycle, you will have some voltage coming up. So this is going to be load voltage. Whereas if I have both diodes open circuited, if both diodes, two diodes open circuited, in that case, neither positive half cycle nor negative half cycle will be able to work. Or if I say these two diodes are open circuited, then only one half cycle will be missing. Rather than that, if I'm going to have similarly these two diodes open circuited, only one half cycle will be missing. But if I'm going to have either these two gone or these two gone, then I'm going to have no output at all. No output at all if both top diodes or both bottom diodes do not conduct or they are open circuited. So you will not have any output at all. But if we say the diagonally opposite two diodes are gone, then at least we will get either positive half cycle or negative half cycle. Okay. So in the next class, we will try to work out a few problems corresponding to the three-phase rectifier as well as single-phase rectifier. And we will say that along with that, we are completing the portions corresponding to rectifier.